Today we are going to study linear approximations and differentials. And here is what we have graphed is some function f of x in blue and its tangent line in red. And you can see that the tangent line in our legend there is labeled L of x. Okay, and that's because L of x we're also going to call our linearization. And all it is it's the tangent line to f at x equals a. Okay. Now, the way that we're going to use this is it's going to help us approximate the function f of x at points that are close to x equals a. And we'll write some of this down here in a minute, but let's try and visualize this. So let's say that this blue curve here, it was really hard to evaluate f of b. Okay, because maybe we're working with some irrational number here, and maybe some function that's just not easy to work with. Okay. Well, if we instead look at the tangent line, as long as we're not very far from where the tangent line intersects the curve, then using the tangent line to approximate this value is going to be a pretty good estimate. So this would be L of b here. And let's just write L of b is a good estimate for f of b when delta x is small. And you might be wondering, what is delta x? Let me move this down and you will see. Delta x is just the distance between a and b. So we're just saying as long as a and b are close, then this linearization or this tangent line is going to be a really good approximation for the function. And let's just formally write down what the linearization actually is here. So the linearization y equals L of x is the tangent line of f of x at x equals a. And the equation for this thing is y equals, or actually let's write our point slope form here first, and then we'll box the answer here. So if we were to come up with the equation of this tangent line, we know we want y minus the y value of the point that we're going to go through. So the y value is f of a. Okay, so y minus f of a is equal to, and if we wanted the slope of the tangent line there, that should be the derivative there. So f prime of a, and then x minus the x value that we're going through, and that would be a. And so all the linearization is if we just solve for y here. So L of x is equal to f of a plus f prime of a times x minus a. There's our linearization. And the next thing I want us to do is we're going to take a peek at our graphing calculator and see why this technique works so well. Now that we're looking at our TI-84 plus here, is what I want us to do is graph y equals sine of x. This is a really curvy function. Okay? And that's specifically why I chose it here. Okay, and is what I'd like you to do is go ahead and hit zoom, and let's zoom in, and we can all kind of choose a different spot here. I'm gonna move up here and try and pick a spot that is a little bit closer to the top. About right here. Okay. So I'm going to go ahead and hit enter and zoom in. And you can see, still looks pretty curvy. Let's go ahead and hit zoom here one more time, and we'll go down to zoom in, and one more time there. All right, and so after zooming in just twice, that is starting to look like a straight line. Let me recenter this and then maybe zoom in one more time. There we go. So I'm going to hit zoom, and I'm going to go down to zoom in, and I'm going to hit enter and enter. All right, and now this does look like a linear line. And no matter which point you chose on this line, y equals sine of x, the same thing happened. You zoomed in, and it started looking like a linear line rather than something that's curvy. And so what this means is essentially, as long as we're zoomed in far enough, the tangent line and the actual curve look almost identical. Example 1, find the linearization of y equals 3x squared minus x at x equals 2. So this first example here is just to give us some practice with this new concept. Okay, and so we want to use that linearization formula, L of x is equal to, and we don't have an f here, we have a y, but that's okay. We would want y of 2 plus y prime of 2 times x minus 2. And so all we need to do is just find what y of 2 and y prime of 2 are, and we'll have our equation. So y of 2, let's just start off with that one. That'd be 3 times 2 squared minus 2. And that's going to give us 10. And then y prime, well, we're not going to find it of 2 yet. We'll find just y prime first. It's 6x minus 1. And so then we could find y prime of 2. It's going to be what? 12 minus 1. So that's 11. All right, and we have everything we need here now. We can go ahead and plug all this in. We have our linearization is equal to y of 2, which again is 10, plus y prime of 2, which is 11, and then x minus 2. And if we were to distribute and combine like terms here, we'll have L of x. I'm going to make a little more space for it though. L of x is equal to 11x minus 12. And then part B, use the linearization to approximate y of 2.1. Okay. Now, here the linearization wasn't extremely helpful to use because y equals 3x squared minus x is already really easy to work with, and it's easy to plug 2.1 into. But this isn't going to be the case when we're working with some other functions, and we'll see an example here shortly. But all we're really being asked to do here when we approximate y of 2.1 is we're just going to find L of 2.1. We're just going to plug 2.1 into our linearization. So this gives us 11 times 2.1 minus 12. And that's going to give us 11.1. All right, and the last thing we're going to look at are some different types of error. And so really, depending on what our application is, will depend on which one of these types of errors we find to be the most useful. One of these is just absolute error. And this is just going to be the actual minus the estimate. And so what this looks like then is, well, we need to go and find the actual value of y of 2.1. Okay. So if we maybe did that over here on the side, y of 2.1, well then we'd have, what, 3 times 2.1 squared minus 2.1, which is going to give us 11.13. So we're going to have 11.13 minus the estimate, which was 11.1. And I'm calling this one here the actual because y equals, let me scoot up here, 3x squared minus x. That was the actual function we were working with to begin with. And I'm calling the other one the estimate because it's just our linearization. It's what we use to make the estimate. And so if we subtract these, let's see here. If we subtract these here, we're going to get 0.03. And then next, we have our relative error. And this is going to be really just your absolute error over the actual value. Okay. And so what that would look like then is actual minus estimate over actual. All right, and so if we do that, well, we have the 0.3 already on top, and the actual was 11.13, and so this gives us a relative error of approximately 0.02695. And then lastly, we have our percent error. And so this one here is just your relative error times 100. And so for us, that just comes out to be approximately 2.695.